everyone, I am Miguel and I am a product manager in Google's privacy team. And today I am excited to talk to you about our differentially private journey. That is the journey that we took that was several years long to produce the differentially private infrastructure that powers a lot of Google's infrastructure nowadays and a lot of use cases. I'll talk to you about some of these cases. This is the agenda that I have for today. I'll basically focus a lot on building the infrastructure, the journey that we embarked on, going from the very basic level pieces to higher level pieces, and also talking to you about some usability aspects that we found in the way. So just to start, I'll let you know that getting to the point where we could build products with differential privacy from the ground up was a long journey. And I think there are three critical pieces that are important in that journey. The first one is building strong foundations. The second one is building frameworks that are familiar to potential users. And the third one is helping users navigate the utility privacy frontier. You know, one of the first questions that we asked ourselves about 3 years ago was, why do we need the infrastructure? Around that time, we started seeing that there was an increasing demand to produce private data. At the same time, differential privacy started to emerge as a very solid privacy guarantee by passing the test of time. Therefore, we started exploring the idea of offering some basic components for internal teams who might be willing to try to use differential privacy. This is how we ended up with the idea of building foundational infrastructure that are the building blocks libraries that power a lot of our internal offerings. Our DP infrastructure starts with the foundational libraries. We started to work in these libraries around 3 years ago. Our vision was to power differentially private use cases that could accelerate developer velocity. Many times, people are just trying to experiment with a new idea. In this ideation stage, differential privacy provides a very good way of getting an idea off the ground by knowing the overall statistical trends, and therefore it allows the developers to start guiding their path towards a product development. The foundational library that we use at Google is the same one that we published and open sourced last summer. For us, it has always been really important to provide transparency around our implementation. We hope that all of you have had the time to poke around with the library. As I said, this library was launched around a year ago. And a few months ago, we also launched a Java and Go version of it, alongside Privacy on Beam, an end-to-end privacy framework that allows developers to compute differential private statistics in an end-to-end manner. You know, in crypto, people say don't roll your own crypto, and that is because there are many pitfalls along the way. We think that this is also good advice for differential privacy. Reusing a hardened implementation is probably a good idea. As you can probably imagine, Google's infrastructure is very complex. So adding differential privacy natively to that infrastructure seemed back in the days like a gargantuan task. We also didn't know if the demand was there for a general availability service for differential privacy. To tackle this uncertainty, we piloted a version of differential privacy for a SQL engine that back then wasn't as widely used at Google. You might think that this was a small task, but it wasn't. A lot of our first users were processing terabytes of data and using those streams of data to produce differentially private results. The second step that we took was to build SQL engines. You might be wondering why we started there. The answer probably has to do with a hunch and demand. SQL continues to be a high productivity data analysis tool over large datasets. Back in 2017, we sensed that there was an increasing need to provide a privacy-preserving way of manipulating data. SQL is quite extensive in its use and easy to ramp up, so it felt like the right choice. I'll now give you a high-level overview of one of such SQL systems. As you can imagine, SQL allows almost anything. Many implementations are Turing complete. So enforcing differential privacy while allowing non-experts in differential privacy to write SQL that they're familiar with was quite a challenge. In particular, queries over events per user ID and changes to cardinality present big challenges. If you're not familiar with differential privacy, suffice it to say that the basis of differential privacy is quantifying the effect that a single user can have on the output. So the heart of a differentially private SQL must have the same property. We split and separate SQL statements into transforms within the scope of a particular user and statements made across the results of those individual transforms across many users. What this means practically is fully SQL compliant transforms of an individual's data, including joins, custom functions, etc. Completely unconstrained SQL, so long as it only occurs within the space of what a user owns and a much more constrained set of cross-user transforms. These cross-user transforms are based on the foundational libraries mentioned earlier and include all the basic statistical functions like mean, median, percentile, etc., while forbidding certain kinds of joins. Finally, though proving differentially private correctness is an essential part of the privacy engineer's mission, model checking provides a baseline level of confidence to the development process. As part of the foundational libraries, we employ stochastic model checking as part of a set of regression testing. While not a sufficient guarantee for differential privacy by itself, it quickly catches violations, both obvious and subtle, and provides a more stable backdrop to traditional privacy verification work. This is an example of a differentially private query. User-centric design was a big component of it. First of all, we want to make sure that a user understands that they are performing a private operation by adding the anonymization keyword. Next, we give users the opportunity to tune some relevant privacy parameters, such as epsilon. The query itself contains the anonymization function, in this example, a count and an average. Configurable per record confidence intervals are also released as part of any aggregated result. You can check out the details of our SQL implementation in this paper that we published and was accepted at PETS. One of the first applications for this infrastructure was a use case driven by social science related topics. About 3 years ago, we wanted to measure the impact of Hurricane Maria in mobility patterns. We partnered with scientists and produced a mobility map that was used as a proxy to measure the impact on mobility in Puerto Rico. Most recently, some of our colleagues published insights into human mobility using the foundational infrastructure we've built. Some more recent examples of products at Google that were built with differential privacy include the mobility reports, and just as of a month ago, the search trends symptom dataset. Now I will talk to you a little bit about the utility privacy frontier. How will differential privacy affect my data? That is perhaps one of the first questions and most common questions that we hear from users trying to produce a differentially private output. This question arises from the fact that when we explain to people what's differential privacy and we tell them that it relies on adding noise, people get somewhat scared about it. So that's why one of the ways that we help users to think about this utility privacy frontier is by plotting the theoretical information gain resulting from applying a specific epsilon. This allows us to make informed choices as part of a privacy review process, but it isn't intended to be a guaranteed statement about outcomes or privacy guarantees. What you're seeing here is information gain that an attacker gets after applying differential privacy. And what you see is that if an attacker has a prior probability of 0.5, guessing whether someone was or wasn't in the dataset after applying differential privacy, their guess only increases to 0.516 up to 0.762. This is one of the ways we help users think about the utility privacy frontier. First, by plotting the theoretical information gain resulting from applying a specific epsilon. This allows us to make informed choices as a part of the review process. We also try to help users produce private statistics that help them understand the consequences of their parameter choices. Our goal is to allow users to make informed decisions, and what you're seeing in this graph is the overlay of the raw distribution of the underlying data with the differentially private distribution of data. Our goal with these types of graphs is to help users tweak some contribution bounds to allow them to extract more utility from their dataset while still preserving some meaningful levels of privacy. We help users produce statistics that help people understand the consequences of their parameter choices. Our goal is to allow users to make informed decisions. Finally, in terms of lessons learned, it really takes a lot of time to build the right DP infrastructure. There are many layers and there are many unknowns that we found out that were super important. Building it in a way that can be used by different use cases really pays off. I show you examples about mobility that we've published, but there are also other use cases that are internal to Google that have been extremely powerful. Third, putting an emphasis on the user is super important. A lot of people don't know what differential privacy is, and they shouldn't. And therefore, our job is to make their job easier. This is a great way to get people to adopt differential privacy. And finally, explaining the privacy utility frontier is key to gather user support, because only if they understand what's happening to their data, they will be convinced that it's the right choice.